In this video, we'll take a look at the properties of an ideal gas. We'll see how to find the gas-specific constant of air that we used in the last video, and we'll see when we can and can't use the ideal gas law. So to start off, we'll look at the properties of an ideal gas. So first, the ideal gas must have a large number of identical molecules. Second, the volume of the molecules must be much less than the volume of the gas. Third, the molecules move randomly. And lastly, the molecules must have perfectly elastic collisions. We'll start by looking at air. So air behaves as an ideal gas. And in the last video we saw that the gas-specific constant of air is equal to the universal gas constant divided by the molar mass of air. And we know that this is equal to 0.287 kilojoules per kilogram Kelvin from that table that we looked at. And the universal gas constant we know is always 8.3145 kilojoules per kilomole Kelvin. So to find that this gas-specific constant of air is equal to 0.287 kilojoules per kilogram Kelvin, we need to find the molar mass of air. And to do that, we have to think about what air consists of. So air is mostly nitrogen gas, so it's 78% nitrogen gas, and it's 21% oxygen gas, so O2, and the last 1% is made up of a lot of different things, but the thing that contributes the most is the 1% of argon. And to find the molar mass of air, we have to take the molar mass of each of these components and multiply by its percentage of makeup to get the molar mass of air. So we'll look at the molar mass of nitrogen gas first. So this is equal to 2 times the molar mass of a single nitrogen. So nitrogen is 14.007 grams per mole. So times 14.007 grams per mole, which gives us 28.014 grams per mole. Moving on to oxygen. So molar mass of oxygen, we also have to multiply by 2 for a similar reason. So for oxygen's molar mass is 15.999 grams per mole. So 15.999 grams per mole, which gives us 31.998 grams per mole. And for argon, we can just directly look in the periodic table, and we find that argon is 39.948. So 30, that's not even close to 3. 39.948 grams per mole. And to find that molar mass of air, we just have to take the percentage of whatever molecule we're looking at multiplied by the molar mass of that molecule. So we'll look at nitrogen first, so 0.78 times the molar mass of nitrogen, so that 28.014 grams per mole, and we'll add the molar mass contribution of oxygen gas, so 0.21 times that 31.998 grams per mole. And we'll finally add that contribution of argon, so plus that 0.01 or 1% times that 39.948 grams per mole, which gets us to, pull out a calculator for this one, 0.78 times 28.014 plus 0.21 times 31.998. Try not to make an entering error, so plus 0.01 times 39.948, enter. So that gets us about 28.97. 28.97 grams per mole. Awesome. So now we can use this to find that gas specific constant of air. And from above, we just said that that was equal to the universal gas constant divided by the molar mass of air. And that gas specific constant, 8.3145 kilojoules per kilomole Kelvin, divided by this molar mass of air that we just found, 28.97 grams per mole. Now let's take a quick look at the units. So kilojoules per kilomole Kelvin on top. And we're dividing by that grams per mole, so we multiply by the reciprocal of moles over grams. So we want this moles right here to cancel out with this kilomoles right here. In order to do that, we have to convert this to kilomoles. And to convert moles to kilomoles, we divide by 1,000. But if we just divide by 1,000, then we get a different unit here. So if we divide the denominator by 1,000 as well, we'll get this, we're essentially just multiplying by 1 right here. It's the same fraction over itself, so that's just equal to 1. So this baby is 1. So if we do divide the numerator and the denominator each by 1,000, we get, so this stays the same, kilojoules per kilomole Kelvin, and then we divide by the numerator by 1,000, so then we get kilomole, and we divide the denominator by 1,000, we get kilogram. So all these K's start looking the same and sounding the same, but we know that this kilomole can cancel with this kilomole, and we get that this is kilojoules per kilogram Kelvin. So we know the unit now, but we don't know the number. And because we multiply by 1 here, the numbers don't change, so we can still enter the same numbers to the calculator. So we get that 8.3145 divided by 28.97. We get 0.287. What a beautiful number. So 0.287 kilojoules per kilogram Kelvin. And this is exactly what was in the table last time, which is pretty cool. Awesome. We'll move on to looking at water next. So water, what a beautiful W. So water, if we imagine water in a box, and let's say that water vapor is in this box. So water vapor is a gas, and we know gases will behave like an ideal gas. So the molecules are moving randomly. The volume of the molecules is much smaller than the volume of the entire gas. And we know that the ideal gas law applies. So now, let's think about the other states. So you can also have water as ice, so a solid. So ice or liquid water. And in these cases, the water molecules are much closer together. And they no longer have those properties of an ideal gas. So they're not moving randomly like a lot, and they might not have those perfectly elastic collisions. So we think maybe the ideal gas law doesn't apply. This is true because if you apply pressure to a solid or a liquid, it doesn't necessarily change the density or the specific volume by a significant amount. So just a reminder that density is equal to mass over volume, and that 1 over density, we defined in the first video, is equal to the specific volume, which we'll denote with a lowercase v. Which is kind of confusing because this is supposed to be an uppercase v, and this is a lowercase v, but this lowercase v is a specific volume. Essentially, the idea is that if you have relatively small changes in pressure, you won't see a significant change in the specific volume. And this graph, which uses data from the engineering toolbox, says exactly that. So it graphs specific volume versus temperature. So specific volumes of water still depends on temperature, but not necessarily on pressure as much so, which I think is pretty neat. Thank you for joining me on this video. I'll see you in the next one.